hilarious. You might not think it's so hilarious. But what we're going to talk about here is we're going to talk about thermal expansion. So obviously, when you heat things up, they can grow and they can also shrink. So thermal expansion, due to rise in temperature of a substance, molecules jiggle faster and move farther apart. That word jiggle is just strange. Um, but that was kind of based on the kinetic molecular theory that we looked at in the last PowerPoint, which was that as things heat up, things move faster. Most substances expand when heated and contract when cooled. And probably the most obvious example of this would be railroad tracks. Railroad tracks that are laid on winter days expand and they can buckle, which would mean like this little turning that they're doing in the slide here. So this little turning here um, in the hot summer. Warming metal lids on glass jars under hot water loosens the lid by more expansion of the lid than the jar. So if it's like that classic old school comedy routine happening in your house and you are unable to get the jar off of your pickle container, it would be a wise idea to put it under hot water because the metal lid of your little mason jar will expand more than the glass will. And that mostly has to do with the amount of surface area and also the type of material that it is. So that can be a way of you proving your strength to that macho man that can't get the pickle jar open. Continuing on, thermal expansion, one of the key places that this plays a role is in construction. For sure, when we look at our bridges, if you go down to the old train bridge, you will see little cutouts that look like a grate like this. The reason that those are there is so that they can slide back and forth to allow for expansion and contraction of the metal. And so basically, during the summer when everything is expanding, you would see these little railways almost filling up the entire area within this little grate. And then during the winter, you'd probably see something more similar to what is present right here. But for sure, when engineers are thinking about how to build even railroad tracks, for example, they actually put little gaps within the railroad tracks to allow them to expand and make contact with one another. Oh, my editing did not work. This is really sad. When stringing telephone lines between poles in the summer, it is advisable to allow the lines to sag, be taut, which means super tight, be close to the ground, or allow ample space for birds. And hopefully you can see that my editing sucks. And the correct answer is that they should be able to sag. Great work, everyone. Everyone got it right. So here's the explanation of that. Telephone lines are longer in a warmer summer and shorter in a cold winter, and hence they sag more on hot summer days than in the winter. If the lines are not strung with enough sag in the summer, they might contract too much and snap during the winter, especially when carrying ice. Just kind of a cool fact about telephone lines for you. Based on the substance that it is, different substances will expand at different rates. So the example here is when the temperature of a bimetallic strip of brass and iron is increased, the greater expansion occurs for the brass strip, which bends to turn a pointer to regulate a valve or to close a switch. And so you can actually direct the way in which these guys are actually going to bend, which is kind of an interesting little feature there. Bimetallic strips are used in heaters, oven thermometers, refrigerators, and electric toasters as well. So just using the properties of materials, you can create some really, really interesting effects. So here is a little formula that we get to use here. There's a better description of it on this next slide here, but when the temperature of a material increases, its length will also increase, and that length is determined by this change, this delta L here. That is the change in length. Delta L is the change in length. And this L0 is the, I'm going to just call it the natural length. The coefficient alpha is the coefficient of linear expansion. That is based on the material. So typical values are between 0.5 times 10 to the minus 6 Kelvin to the power of -1 and 10 times 10 to the -6 Kelvin to the -1 at room temperature. If it's a solid, it is going to expand in every direction. So if we were to heat this solid, we would expect it to expand in absolutely every single direction. So here is, like I said, that better description of that formula. So delta L being the change in length, delta T being the change in temperature, so what it was previously versus what it is now, and then A being the coefficient of linear expansion. I said that this is based on the material that is being used. Okay, so accounting for thermal expansion changes. The steel bed of a suspension bridge is 200 meters long at 20 degrees Celsius. If the temperature goes from -30 degrees Celsius to +40 degrees Celsius, what contraction and expansion is possible? And so we would want to use then this formula over here. And so again, this value here would be given to us. This 12 times 12 times 10 to the -6 Celsius to the -1. We would multiply that by 200 meters, which I said was the natural or original length. And then where this -50 is coming from is this is saying we built the bridge at 20 degrees Celsius, and we said it can go all the way down to -30 degrees Celsius. So this difference is -50 degrees Celsius, which is why that value is being plugged in there. So what's interesting is that length will shorten. This is a negative value, so that means that it's getting smaller. This length will shorten by 0.12 meters, which is the same thing as saying this will shorten by 12 centimeters. That's quite a big difference in terms of how much it's shortening. It's almost half a foot. And then in the summer, well, there's not much of a change because we built at 20 degrees Celsius. We said it could go up to 40 degrees Celsius. So again, a difference of 20 degrees. In this case, it's a plus 20 degrees because it's getting hotter. And so there we can figure out that the length, this one's only going to expand 4.8 or 5 centimeters or 0.048 meters. So this is the New River Gorge Bridge in West Virginia. This is a steel arch bridge, which is 518 meters in length. We were given the alpha value here. We were given the coefficient right there. How much does it change between the temperatures extremes of -20 degrees Celsius and 35 degrees Celsius? Well, we don't actually know what the original temperature was. We don't know what it was, so we're going to assume it was built at, we can assume it was built at 0 degrees Celsius. And so what we're going to do then is we would take our delta L is equal to alpha L0 delta T. We're going to take this formula here, and we're just going to plug in some of the variables. So note, we'll have to do this twice. We'll have to do it for the absolute coldest temperature, and we'll have to do it for the absolute hottest temperature. So we want to find the change in length. We know that the coefficient is 11 times 10 to the -6. We know that the natural length was 518 meters. And we're going to say that this change in temperature, let's do this for the cold one. This would be the cold calculation, was -20. Plugging those values in when you punch the numbers in on your calculator. You should get a length difference of -0.11396 meters. So that's for when it gets cold. When it gets hot, we have to do another calculation, and we'll do delta L is equal to alpha L0. This is called naught, so it'd be L naught delta T delta L is equal to 11 times 10 to the negative 6. L naught was 518 meters. And, oops, this change in temperature will be plus 35. Multiplying those together, 11 times 10 to the negative 6 times 518 times 35. This bridge is going to expand 0.19943 meters, like so. So it's shrinking in the winter 11 centimeters and expanding in the summer 20 centimeters, which is quite a big change. And so what can actually happen as well is we can actually have the expansion of water as well. So when water becomes ice, it actually expands. Water is unique in that sense. Generally speaking, this is opposite of normal. Because what we said was that as something got colder, it would shrink. As something got hotter, it would expand. The problem with ice is that that is not true for water. And what ice actually does is it has an open structured crystals that result from strong bonds at certain angles, and it increases its volume and thus makes the ice less dense. Kind of the example that I like to think of is if you've ever had like an ice tray and you filled it up what you thought was almost perfect. So you filled up each of the little ice cube trays almost perfectly. You would put that in the freezer and pull it out, and for some reason every time you do that there's a layer of ice connecting each of the individual cubes, and that is because the ice is actually expanding. It wants to form this structure here because this is more stable, and that's why ice appears as a solid. Now what we do in Saskatchewan is, because we get really, really icy roads, what we do is we put sand or we put salt on the roads. And what sand and salt do is they're actually little particles that try to jump in and interrupt the process of these bonds being formed. So it tries to stop ice from actually forming a solid. And so that's why we actually put sand on the roads. Additionally, sand has the benefit of it helps our tires grip on the actual ice itself. So it does a twofold purpose. Now, I'm going to flip over to this. Can you guys see these videos if I flip over to them? Okay, awesome. Thank you. Okay, so this is me doing an experiment. Okay, ignore my laughter. So that's one of the experiments that I've done before, and here is another one. Oh man, the audio is super worth it. You can't hear the audio, really? Really? Oh, I know why you can't hear the audio. Yeah, that makes sense. These are posted to Google Classroom, so you can watch them later. But basically what's happening is I'm taking this water, which I was really young here. Wow. I'm taking this water. It had been in the freezer for, I think, just over 2 hours. Yeah, because it had been there for just over 2 hours, it was actually at a temperature of -4 degrees Celsius, which for water, that would mean that it is ice. But because it's in a pressurized water bottle, it actually cannot become, it can't actually become ice when it's in that state. So what you'll notice with this one here is I'm pouring it on the actual ice itself, and it's forming another layer of ice the second that it comes into contact with the ice cubes that I had in that bowl. And the reason for that is it's at -4 degrees Celsius. It needs something to interrupt or to relieve the pressure of it being in the state of water in order for it to transform to ice. So this example is a little bit better, but this is completely water right now. And as soon as I slam this water bottle onto the table, and interrupt the pressure or increase the pressure within the water bottle, it changes the stability of this water. So it can't remain water anymore because I'm puncturing the water bottle and basically making it have an imperfection. And so that allows it to rapidly form ice immediately when I slam it down onto the table. So if you have a water bottle lying around your house, you can try this. You want to freeze it for about 2-ish hours. And then when you pull it out, I'll actually go back to that video. I'll show you when you pull it out. I did this with like 2 or 3 different water bottles. If you look at, hold on, let me get to this. If you look at these 2 water bottles on the left here, if you look at these 2 on the left, those 2 are actually, they've already started freezing. And so that's when I knew that these 2 water bottles on the right would be the perfect temperature to do this with. You want to have it basically right at the threshold between freezing and right at the threshold between being still a liquid. All right, so that's that experiment there. And so the last 2 slides here, talking about the thermal expansion of water. We would have done that experiment in class, so I'm a little sad that we don't get the chance to do so. We would have made slushies. You can add some flavoring and some food coloring to those things and make them slushies, and we would have done that. So sad times we don't get to do that. We'll maybe have to do that if you guys take Chem 30. So thermal expansion of water. When ice freezes to become solid ice, it increases in its volume tremendously, and as the solid ice cools further, it contracts. The density of ice at any temperature is much lower than the density of water, and that is also part of the reason why ice floats on water. And then the last slide here. As water cools, it sinks until the entire pond is 4 degrees Celsius, and then as the water at the surface is cooled further, it floats on top and it can freeze. Once it is formed, temperatures lower than 4 degrees Celsius can extend below the pond. And life continues, just like this little fishy. Yeah. So that is Physical Science 20 today. We will reconvene at 2 o'clock for some mathematique.